Okay, let's consider the following problem. That we are sending a projectile from the Earth surface with a velocity v0 and angled alpha. And there is a trajectory, and after a while the projectile will come back to the surface of the Earth. And we would like to calculate the maximum distance from the center of the Earth to the projectile particle, the rmax. What is that distance? We know that it's the Earth radius from the start. And we also get this equation that v0, that speed, equals gm, Earth mass, divided by Earth radius, square root of that. So how are we gonna tackle this one? Well, let's see. Could it be that the mechanical energy is conserved in this case? And the answer is yes, because the forces we have in the system here are gravitational forces, and those are known to be conservative forces. The way to check that is to take the rotation of the force expression and show that that's zero. Then we know that the force is a conservative force, and then we know that potential energy exists. And if potential energy exists, then the mechanical energy is conserved. So E here is a constant. And here, instead of treating this problem as two particles, one body with mass capital M and the projectile with the mass m, we immediately replace that problem with the one particle problem. Yeah, so then we're gonna deal with the reduced mass and its particular speed. And the gravitational potential is a g times the total mass in the center, which is in this case m plus m, and multiplied with the other mass, the reduced mass, and divided by r. And that is the distance between Earth center and the projectile. That's r over here. So then we can set up the system here. What is the energy at that point? Yeah, you have the speed v0, so the kinetic energy is that, and we would know the distance r is the Earth radius. So yeah, then we have this expression here, and at rmax, then you have another kinetic energy. We can see here that this is the turning point. So that the speed in the r direction is zero. There is only speed in the phi direction. That's why I call it v phi here. And again, minus gmm times reduced mass and divided by the maximum distance. So yeah, then we have an interesting equation that might be useful. And this one we should remember also, v0 equal this one. And let's take a look at the torque with respect to this point A, which is in the center of the Earth. Well, not exactly. It is that point is actually where we have the origin, and that is where the total mass m plus m, this one here, is situated. Since we replaced the problem here. So the origin is m plus m, and the orbiting projectile has a reduced mass. So anyway, the torque with respect to that point A, that can be calculated by vector products. And here, the first mass m plus m, this one, yeah, okay. So there is a force here, but the r vector, the position vector r, is 0 because we placed the origin here. So it doesn't contribute to the torque with respect to the point A. So then we go here, and then you have, okay, then you have a vector r, for example, here, and then a force back, or maybe here, and a force back for the projectile, or the reduced mass. So it will be in this way, a vector from this point A pointing to the projectile, and the force will be in the negative direction, or direction. So from a vector perspective, we can write it like this, and it turns out that parallel vectors or antiparallel vectors in a vector product, that will just be 0. And then we have a famous rule saying that the derivative of the angular momentum vector, this one, equal the torque with respect to the same point. And since this is 0, then we know that this here can only be 0 if the angular momentum vector itself is a constant. So that's what we have shown here. Okay, use this expression that it's a constant, or what we sometimes in physics say it's conserved. It's the same thing for all times. So here is the angular momentum from here to the reduced mass, r, vector product, v, and the reduced mass velocity. And r here is still the distance between the original particles, capital M and M. So this is just the equivalent way of solving the problem. And yeah, well, then you can see here that there is the angular momentum here, but the parallel vector will not contribute. So it is that part of the vector v0 that will contribute, and that is v0 sine alpha times the radius, v0 sine alpha, radius, and then also the times the reduced mass. And here, the other side here, rmax, and then you have orthogonal velocity here already. So it is just rmax times v phi times the reduced mass. So then you have this, and you can solve what is the velocity v phi in known quantities. Well, and we have this one. And by using equation 1, 2, 3, we get an expression, and which is a little bit complicated. And to simplify things, let's assume that the mass of the projectile is very small compared to the mass of the Earth. So use that fact 4, and then we get simpler equations leading immediately to the result rmax equal the radius plus this expression. Minus it cannot be, because it must be larger than the Earth radius, as you can see in the figure here. If that's for, then of course that is bigger all the time. So okay, and then the problem text says if alpha equals 60 degrees, yeah, then it should be some value for rmax, and sine alpha for 60 degrees is just this one. So this factor here will be that, and then you get this, and you get the 3/2 of the Earth radius, what you see here. So that's that. That problem is solved. So just for fun, one can solve it much more accurate by not doing the approximation that the projectile mass is very small. If we don't do that approximation, then we end up with this full expression that is valid for any mass m or capital M. So a little bit more complicated expression, as you can see. And we can check it. Yeah, okay, but if the projectile mass is very small, so let this go to 0. And then you see, yeah, okay, if that is 0 or that is 0, so m, yeah, that will be 1. Okay, and here then this will be small, and those guys here will also be disappearing. So it will just be minus 3/4. So you get this, and then you get 3/2 the radius. So yeah, this formula checks out for this example. And just for fun, let's assume now that instead of the projectile mass being small, let's suppose the Earth mass is small instead. So capital M goes to 0. And then you see, okay, this is not important, so it's just those two. So that will be 1/2, right? And then the radius, and if you look in here, the capital M will be 0. So this expression here will be 0. And your left, that is 0, and your left 0 divided by m squared, which is the number, so that will be 0. So that will be 1. You don't get any contribution from that. So you get this 1 plus 1, yeah, and so you get RE. So that's funny. The maximum distance is then the same if the Earth mass is small. So how can you understand this? And it's actually, one has to realize that the speed v0 is equal to gm something. And if m, the capital M, Earth mass, is almost 0, what will the speed be? Yeah, that will be 0 too. So in fact, then we start with a situation that, yeah, the projectile is not moving at all. So it will remain in the position radius, Earth radius, for all times. So of course then the rmax is also the same as the Earth radius. So that was a little fun fact following automatically from the full formula. And just for fun, okay, let's consider if Earth mass and projectile mass are equal. So what can that factor here then be? Okay, so that we can write as 2m, that you can write as 3m, so that's 2/3. Okay, so it's 2/3 here. Then you have this complicated one here. So that is 1/3m squared. Yeah, okay. And here's 1 and plus 2 plus 1. So that's 4m squared. So it's 3/4. So you have 1 minus 3/4 times 3/4. So, yeah, okay. So that will be 9/16. So what you get is this rmax equal 2/3 or radius, and this 16/16 is a simplification of 1 here. So you can now take 16 minus 9, that's 7. Okay, and 7/16 square root, yeah, that's square root 7, and divided by 4. So that is about 1.11 Earth radius. So if the masses are similar in size, then it won't move so much, so high, as when it was a small mass. Yep, so hope you enjoyed this lesson. So see you later. Bye bye.